But if we're looking for living planets, or life, planets that could actually have life, we actually need water, liquid water, because that's what we know about. So, if a planet is too close to the sun, like Venus, it cooks. It burns up all the water, it bakes everything. If it's too far away, it freezes, like Mars. To have liquid water and potential of life, you've got to be in that intermediate zone, what we call the habitable zone, or the Goldilocks zone. Just the right distance, just the right size, and the right distance from the star. And if we find a planet there, that is the place we need to look for life. So, if we think about that infrared spectrum, that idea I spoke about earlier, here is the infrared spectrum of 3 planets we know an awful lot about. You can see these dips and wiggles. And each one of these means that there's carbon dioxide, there's ozone, and there's water. Look how different those 3 spectra look for these planets. Which planets are they? Well, the first one is Venus, the second one is Mars, and only the third one has life, that middle one. In the Goldilocks zone, our Goldilocks zone, Earth. And so if we can take the infrared spectra and find this pattern and find planets in the Goldilocks zone, that is our first step. It turns out with the James Webb Space Telescope, we can actually, this is a simulation, we can actually capture small Earth-like planets transiting in front of stars and look through that bit of atmosphere, that glint. And the James Webb Space Telescope is large enough that it may be able to take this spectrum and find liquid water. So James Webb Space Telescope has the potential to discover water worlds, liquid water. And that's the promise, one thing we can do. So in 2018, we're hoping to launch this amazing spacecraft, and it will look out into the universe in new ways. But it will also begin to challenge the way we think about things and the universe. As the famous evolutionary biologist said recently, he was asked, what is the most important experiment in modern biology today? And he answered, the search for extraterrestrial life. Did evolution happen elsewhere in the universe? Or was it a chance event that only happened here? More profoundly, if we find life, it'll be as profound as Darwin and Copernicus rolled into one, because it will bring about an irreversible change in our worldview, because everybody will be able to see evidence of life around another planet and realize that we're not as special as we thought, that evolution happened elsewhere, and in fact, we perhaps live in a very different universe than our previous generations thought. The James Webb Space Telescope makes it possible that this generation, our generation, becomes that time when we make that step at which there is no return, the realization that we're no longer alone.
Thank you, Matt. So I'm going to continue. So Matt basically told you something very, very interesting, is that he told you that the James Webb Space Telescope has the potential to discover wormholes, which is an incredible statement to make. And I think people would be very excited if that's the only thing a Webb could do. A Webb can do much, much more than this, and it turns out it's a very, very versatile instrument. And I'm going to tell you a little bit about what the other things we hope to do with the James Webb Space Telescope. And so to explain it to you, to cast it in the proper light, I think we have to tell you what Webb was really built to do. So Webb is really all about beginnings. So what we really want to do is we want to learn how the first galaxies ever formed. We really want to know what that process was. We want to know how those stars form in those galaxies. But we want to go even further. We want to know how the first stars ever in the universe formed. And then, as Matt mentioned, we want to find perhaps the presence of life or hints of life. But in order to do that, we need to find, for example, the planet that might harbor life. So we want to find the beginning of how planets actually form. So in one sentence, basically, we're going to build Webb because we want to go beyond what Hubble can reach. And so the four themes of science that we want to address with the Webb Space Telescope are relatively simple. And as always, when we have, when we try to, answer simple questions, the answers are actually much more complicated than we can imagine. But these are the questions we want to answer. I'm going to address a few of those, the ones that Matt has addressed, which is the galaxy evolution, planet formation, and the first stars. Ultimately, we build telescopes, and Matt has been doing this for a very long time, because they're time machines. They tell us about how the universe came to be, they tell us about how nature works, and we're interested in pursuing that. We have a model that works very well so far about how the universe came to be. And so we built Webb to tell us basically how galaxies and stars and came to be, and how from very humble beginnings, if you will, they all came to be as large as we are, with hundreds of billions of stars for as far as galaxy is concerned. So this is a simulation that shows you how we think structure in the universe grows, and how the first stars are being born in the universe just due to the effect of gravity. So there's nothing else other than gravity and processes that are being shown here that are related to how the gas heats up, how stars are being formed. So you see this accretion process is something very, very common in the universe, and we would like to understand exactly how do we produce the first stars, how do we produce the first galaxies, what are the processes that lead to that. And to do that, we need, because the universe is expanding, we need the infrared. We need to look at the infrared, which is actually quite convenient because in order to find planets, we also need the infrared. What we want to do is, you see an Hubble image at the bottom of a very nice part of the galaxy, which is interacting with another galaxy. But at the top, you see something that we can do with another infrared telescope, a much smaller telescope. But you see, it's a little fuzzy. It has, you can see stars in it. It's very, very fuzzy because the size of the telescopes is actually much smaller than what we're going to have with Webb. So what I'm going to try to tell you is that what we want to do is to have the same resolution you see at the bottom that we have with Hubble, but in the infrared. And why do we want to do that? Well, we want to do that because we want to tell something more than just the stars and the galaxies. We want to show the process. We want to see galaxies being born and grow from infancy to adulthood, if you will. This is another simulation we can run. We can run simulations that put particles and let gravity do its work. So you see two galaxies meshing into each other. That's how galaxies accrete material and age, if you will. You see spiral arms being born. You see bars being born. You see now galaxies turning around and coming together. So we cannot run an experiment like this because it would take billions of years for us to wait. But we have lots of galaxies in the universe. We have billions of galaxies in the universe. And so we can take a snapshot at any given time and take a look at the life of these galaxies from their infancy to their adulthood, basically. So you see, for example, gases being injected, galaxies are changing shape due to mergers, and this is something that we really look forward. You see things being ejected because the velocity which is higher than the gravitational potential of both stars. And ultimately, what we want to do is we want to look at, as Matt said, a very, very tiny patch of the sky where we find thousands and thousands of galaxies that Hubble has looked at. But we want to look further. We cannot look at the first galaxy with Hubble because we don't have the right eyes, if you will. We have to go beyond that. And so if we take this picture, we can simulate what Webb will look like. You're going to see the emergence of a gigantic number of galaxies, just very small galaxies that are in the process of being formed. And you can also see that even the current galaxies that we know of actually are much more extended in the infrared than they are in the visible. Ultimately, as Matt said, we want to look for life. We need to look for planets, and in order to find planets, we know planets are usually around stars. And so what we want to do is we want to do something like this. We want to go to an optical image to an infrared image. This is again a Spitzer image, so we're going to have a better resolution image of this. But the idea is that we can basically see thousands and thousands of stars embedded in gas clouds just because we have the right set of eyes, if you will. Here's another spectacular image from Hubble. You actually notice something I'm going to show you a little bit later, which is the jet on the far left from a star-forming region. But we don't know what's inside the star-forming region, what stars are being born in there. We could if we had infrared eyes, and so Hubble is equipped with some infrared instruments, and so we can actually remove a little bit of that shroud of dust. Let me give another example, which is pretty astonishing again. This is another nebula where we know there are stars being born, and we know a little bit more about this nebula because we can actually see
in the initial formation processes that lead to the formation of disks around other stars. So we think that those little disks, the dust disks, actually do harbor potential planets. So this is the place where we want to look at. And if we want to look for life, if we want to look for the formation of planets, we need to look in the infrared because we can remove that shroud. Ultimately, as I showed you before, we can look at stars. This is an artist's rendition, obviously, but we can look at those disks and find the planets that are being harbored, and the planets that are being born in those disks. And the idea is that what we really want to do, again, like we did for galaxies, we want to take a look at the formation process that leads to the formation of these planets. And again, in the early formation processes of planetary disks are enshrouded by this dust, by this infrared dust. And so if we want to be able to see these knots that you see forming around the simulated star, we need to be able to lift that shroud. And this is exactly what the Webb Telescope is built for. So I'm going to conclude. My remarks are very quick, but these are the four things we want to do with the James Webb Space Telescope. We want to look for the signature of the first star to ever formed in the universe using Webb as a time machine. We want to look at the formation of planets inside, around these stars. We wanted to look at how galaxies evolve over time. And ultimately, we do want to find these water worlds that are things that are perhaps transforming, as far as a species. So I'm going to leave it. Thank you.
Thank you. So now that you've heard about all the incredible things that Matt and Alberto are describing about what the scientists around the country need to do for the next generation of science, the other side of the equation is, what does it take to make that possible? So we look at some of the things that Matt and Alberto talked about. You needed a telescope. Oops. And it's on secret. Thank you. So some of the things that Alberto was just talking about ends up translating into a telescope 100 times more powerful than the Hubble Space Telescope. And one of the interesting things when you talk about a telescope's power ends up being the size of the mirror. And the way I think about it in terms of why do you need such a big mirror is, if you go outside, for example, and it's raining, and you took a coffee canister and put it outside on the ground, it rains overnight, and you wake up the next morning and look inside the coffee can, and let's say you had 2 inches of water inside the coffee can. Now, if you put next to the coffee can, let's say a kiddie pool, about this big around, and let that fill up with rain the same night, you would also have 2 inches of water. But the kiddie pool has a lot more water in it. And the same thing's happening with photons with light. If you have a bigger collecting bucket to capture that light, you're able to have more photons and therefore see those extremely faint objects that Alberto was talking about. The other thing about having a big telescope is they get heavier. And of course, we're talking about putting something into space. And the annoying thing about space is that you have to deal with Earth's gravity. So as the telescope gets bigger and bigger, the engineers are having to figure out, how do we make it light enough that we can get it into space? The other issue, of course, is it becomes so big it doesn't fit inside the inside of a rocket. So if you're going to have an extremely large mirror, how are you going to get that so that it fits inside some kind of vehicle that can get it off the Earth and into its orbit? Alberto made a point of talking about infrared light. Infrared light, of course, is sort of like heat. And if you've ever seen, ever tried them yourself or seen a picture of somebody using night vision goggles, if they're looking around in the dark, you can see the heat signature of the people that you can't see with your eyes. And of course, if you wear night vision goggles during the day, it'd probably be very unpleasant for your eyes. And just like that for James Webb Space Telescope, it doesn't want to see heat since it's looking for heat. So it wants to be in a place that's extremely cold. And that engineering-wise became something very important for the design of the telescope. So then, the next issue is, how do you answer those challenges now that you know what you want? I talked about the fact that you need an extremely big mirror, but it had to fit inside of a rocket. So you end up looking at ways that you can have a mirror that folds. And I'm going to show you a picture next of what that ended up looking like. If you're going to have something that's extremely cold, one of the big issues is, how is that going to behave? When you build something extremely large, that has to have a mirror that's incredibly precise. You need to make sure that the structure that's holding those things isn't wobbly and it behaves in a predictable way. So one of the things when you think about when you're making a space telescope, you want to put the right prescription into the mirror so that it has sharp vision. But of course you say, okay, well let's figure out what the prescription is and we'll just do it that way. But of course, as you're sitting there manufacturing that mirror on the surface of the Earth, you have a whole lot of gravity pulling down and bending on that structure. And with the bigger and bigger you make a smooth structure, the more gravity starts to matter. Once you put that mirror into space, the gravity's gone. So not only do you have to have the perfect prescription on your mirror, but it has to be perfectly wrong, such that when you put it into space and the gravity's gone, it will bend back into the exact shape you want it to be into. And figuring out how to do that is quite complicated. So here we go. Here's the design that came out with the engineering team working alongside the science team that's not just at NASA and not just at US institutions, but at the European Space Agency and all of the partner countries, at the Canadian Space Agency as well. So it's an international collaboration. It took all the world's experts coming together to think about how can you design the telescope that's going to be able to complete this mission. And as Matt pointed out when he was speaking, it doesn't look like a telescope. And I hope you can come across the river and see for your own eyes the full-scale James Webb Space Telescope. It's 4 stories tall. It's 80 feet long on the sun shield at the bottom. Come up and stand next to yourself. The pictures just don't do it justice. But you think about a telescope, think of a long tube with a piece of glass at one end, put your eye at the other end. And what's the deal with this? I tell you, we set up our full-scale model one time in Battery Park in the southern tip of Manhattan. We got some really interesting commentary about what folks thought that was. That's always kind of fun. But that's all part of what went into what's it going to take to be able to make a mirror this large and this cold. So I'm going to talk a little bit about some of those different components. But one of the big things was we absolutely need to have a mirror this large in order to have the right sensitivity, but the largest rockets we have, it doesn't fit. So right away you knew it was going to have to fold. This is a picture of the telescope folded up inside the Ariane 5 launch vehicle. The Ariane 5 is provided by the European Space Agency. So you can see it's tucked in their side. Now, something different you can see right away is instead of all 18 segments of 18 hexagons of that mirror staring right at you, as you can see on the far right, 3 of those hexagons are folded down, sort of like the leaves on a dining room table when it's stowed, when it's not Thanksgiving. At least my house. Now this is an animation. When you take that stowed telescope, the way it sits inside the rocket, and unfolding it like a flower. Now, it's all good fun to show the computer animation, but actually figuring out how this process works precisely and exactly takes a lot of engineering and technology development. You can see now as the animation continues how the sides of that sun shield material are slowly being pulled out and deployed. Those 3 layers, and now you see it popping up on the top layer, and the different 5 layers of the sun shield start moving up the sides of those deployable booms and pulling out tight. And I can tell you from talking to some of the sun shield membrane engineers that it's not easy to take something that's 80 feet long and keep it completely tight. If you can imagine a bed sheet, not even a fitted sheet, but a flat sheet, that's 80 feet long, and having your friends stand at all the corners and pull it as tight as they can and try to get it exactly flat. Even if you have everyone standing there pulling it, you can imagine the middle section of that sheet, if it was 80 feet long, it's very hard to get the tension right, such that that's completely flat. And that's one of the things that the engineers are taking their time to try to manufacture. It's hard to see in this picture, but that center section of that top membrane, where there's that deployable tower where the mirror is attached, it's not even a flat surface. It's actually a hyperbolic or a curved structure. And that curvature was all designed so that when photons are hitting the hot side of the observatory, they're going to be encouraged to go away from the cold eyeballs of the telescope where you don't want them to hit. Let's see here. So this is a look at the orbit of the James Webb Space Telescope. This is one of the other major things that's different between the Hubble Space Telescope and the James Webb Space Telescope. The Hubble Space Telescope, which Matt showed you pictures of, We talked about the orbit. As he said, it's orbiting around the Earth. And that was wonderful because astronauts were able to take the space shuttle to its extremes, dock with that Hubble Space Telescope, make repairs. But the problem was it was really close to the Earth, a couple hundred miles from the surface of the Earth. Like we said in the beginning, since James Webb is so worried about that heat that makes its night vision goggles not work, the idea was to put it in a much, much farther away orbit. So instead of a couple hundred miles away from the Earth, it's 1 million miles away from the Earth. So once it's out there for good. And it's a great place to take pictures of extremely faint things because it's very dark and very cold. Now, speaking of temperatures, this graphic shows you what we call, in technical terms, the hot side and the cold side of James Webb Space Telescope. And again, one of the things that makes this so challenging is if you can read the numbers on that chart, the hot side where the sun and the reflection off the Earth and the moon are hitting the spacecraft can get up to 185 degrees Fahrenheit. And just on the other side, it's down to negative 388 degrees Fahrenheit. It's a huge temperature change. And once you start talking on those types of changes in temperature, you have to really start wondering, okay, I have this piece and I have this piece. If I glue those things together, what's glue gonna do when you change the temperature by that many hundreds of degrees? You know, if anyone has an old house where their windows and doors start shifting in the wintertime, you can only imagine if your house got to be negative 388 degrees Fahrenheit, and how some of the behaviors and materials become a very significant factor when you're talking about something that has to be so precise. A little side anecdote was that, you know, we talked a lot about the mirrors, they're shiny and gold, testing them is a big deal, but we also had to design a test stand, some actual physical structure to hold those mirrors while they were doing the testing. So then it became, well, that test stand has to be, we have to very well understand how precise that structure is. And there's a small family-owned business in upstate New York that builds large-scale structures. And this company is called JPW. They typically would build things like staircases for a baseball stadium and other types of structures like that. And the NASA came to them and said, we need you to build a big steel structure that can hold our mirrors. And by the way, our mirrors have to be precise down to the scales of, you know, billionths of a meter. And that team of people in that small family-owned business had to learn how to do something more precise than they'd ever done as a company. And as a result, that team of people now has this skill set that they didn't have before they were part of the program. And so it's a story that we see on and on as we go through these engineering challenges, that we have challenges that have never been tackled, they have never been solved. A team of people comes together, they're trained to do something that they actually never done before. And that ended up leading to new things being invented. And not only is that great for the telescope, but it ends up being things that you can use in other ways. Now that company is able to do precision structures, and that opens up a whole lot of different business areas for them. On the mirror side of our telescope, we talked about, you know, having to be able to build these mirrors with such an accurate prescription, but you also have to be able to know that you got it to that accurate prescription, so you have to have a way of measuring those mirrors. So they invented a whole way using something really complicated involving different lasers and different metrology. And it turned out they're able to use that mechanism of measuring those mirrors and apply it to human eyes. And right now, doctors are using that exact same methodology to treat patients and better diagnose ocular disease. And it's just the way that when you're really working on the cutting edge of technology, you make new discoveries, not just on the science side, but on the technology side. And those are things that have very broad-reaching benefits that you don't necessarily see before you start. I'm going to show you now just quickly a couple of pictures of the real hardware. Everything you've seen so far has been animations and graphics, but this is a real sun-shield membrane. So that trampoline-looking layered structure on the bottom of the telescope, this is the real thing in Huntsville, Alabama, a company called Mantech Dexol, and you can see the person there standing next to it. And the other thing you can see with the real thing that's not totally obvious in the animation is that there's little seams running all through the membrane. So there's about 100,000 different welds all through this material. Here's another look at those 5 layers of the sun-shield membrane. This is a much earlier prototype, and the engineers there from Northrop Grumman are looking at those tension points. And it's not just making these layers, but how do you handle those layers? Because if you make them perfect, but then you throw them in a box and pull them out and you wreck them. It doesn't do you any good. So there's a lot of work going into how do you fold those up in a way that you're not putting any folds or creases into them, since all those things are going to end up messing up what you're trying to do, which is smoothly encourage photons to go away from the cold side of the observatory. This is another look at the actual flight mirrors for JWST, and you can see that there's little holes all through the mirror. Just kidding, those aren't really holes in the mirror. That's just the reflection of dots that are on the wall of the test facility. That shows you how crisp those mirrors are. And they're coming out 6 at a time from a cryovacuum chamber at NASA Marshall Space Flight Center. This next picture you can see, they tried out those same 6 beryllium mirrors with one of them coated with gold. And you might wonder, well, how come they're only testing 6 of them at a time? And I'll get to that in 1 second. I just want to show you one more picture of a mirror segment with its gold coating. And as you can see, it looks very smooth. But it's hard to grasp when you talk about nanometers how smooth we're really talking. So one of our scientists from the Space Telescope Science Institute had a great analogy that I will steal right now, which is that if you took one of these hexagons, there's 18, if you took one and stretched it out to the size of the state of Texas, the biggest bump across the state of Texas would be 1 centimeter tall. Pretty incredible. So why do we only test 6 mirrors at a time? Because that's all that fits inside the cryovacuum chamber. So you needed a much, much bigger chamber. So obviously we came to Texas for that. This is a picture inside the NASA Johnson Space Center. Look really closely at this picture, and you'll see something at the bottom of that door that's open. 2 people. One was pointing like that. That's a really big cryovacuum chamber. This was used in the Apollo era. It's a man-rated chamber, and they put the Apollo capsules in there to understand how that structure would behave at extreme temperature changes. Here's a better picture of the door open. You can see all the people that are on the bottom. So they took this chamber that hadn't been used since the Apollo program, able to retrofit and refurbish it such that it would be appropriate to put the James Webb Space Telescope optics inside, and so that we could take the real hardware and have it experience the temperature fluctuations that it will really have in real life. Even a chamber this big is not big enough for the fully deployed sun shield, the 80-foot long sun shield. There is no chamber big enough for that. So that means, again, engineering-wise, a lot more mathematical modeling, scale testing, and verification that we do in order to make sure everything will work the first time. Thank you.
So I'm going to be talking a bit about all the data that is going to be collected by James Webb, as well as the other types of telescopes, and how we've sort of pioneered a new way of distributing this data. Well, it all starts back a long time ago when astronomers first started looking at the sky, even before telescopes. They would make their observations, and at that early stage, sometimes astronomy and astrology were not all that far apart. People would look to try to predict where the planets would be, making tables of the sky. And these tables and this private data that they collected, this was their trade, this was their secrets, this was their the product of their work. And what made them powerful was the knowledge of this secret information that they had calculated. Over time, as that grew, the secrets became stored as glass plates in a university vault, or individual scientists would make his observations and then maybe spend his entire career just analyzing those observations and making theories about it and working that out. As time progressed, the volume of data in astronomy grew and grew and grew, and as the computer era came in, you had chips that were taking massive amounts of information in just a single exposure, and no longer could the data that was collected by these programs be analyzed by just one astronomer. And the program started shifting to be more of a data-oriented exploration, and so that there were missions that would go out and collect this data, and then astronomers would then use these missions together with other mission data and start processing that together. So about 12 years ago, as the Sloan Digital Sky Survey started coming together, a couple of scientists, a research scientist from Microsoft named Jim Gray and Alex Allais from the Johns Hopkins University wrote a paper called the Worldwide Telescope about showing how this fundamental change to a computer science-oriented collection of data, and saying that we really should make the internet a worldwide telescope to be able to put all this data from all these different programs and make it available to everybody to be able to study. And so, unfortunately, Jim Gray is no longer with us, but as a tribute to his idea, Curtis Wong and I, along with Jim's help before he disappeared, put together a program that then was embraced by people like Space Telescope and Caltech and Harvard and Adler Planetarium, many other universities, planetariums, and we wanted to create this tool to reach people for research scientists, for educators and outreach personnel, and also just make it available to the general public. We've shipped our first release in about 2008. We have about 10 million people using the product, and while that's the most highly distributed Microsoft research project ever, it's still not enough for me. I'd like to see it in every school district because it's free, and we want to be able to have this out. So one of the things that we like to do is take the technology that we develop in Microsoft Research and demonstrate some of the capabilities of what can be done with this. So I'm going to break free of this mic here and move back out here, where I'm going to control the universe with my hands. So this is using Microsoft Connect. And now we're flying around in orbit around the International Space Station. I'm using the Connect's gestures to be able to zoom in, and we can look at the habitation modules, the arms. I can also give it voice commands. So I can say, time, real time. We can move away from the Earth, and we can see right here that besides the International Space Station, which is our permanent manned facility in which many countries of the world are providing astronauts and services and experiments up, we also have a lot of other satellites up there. And we can see one in low Earth orbit, and some very elliptical orbits, and then the green ones are communication satellites to give us TV and international phone calls. Coming away from here, we can see that it's a little hard to find planets and stars and things like that just by looking at them. So we'll get some help here. Orbits on. And here now we can see the orbits of these planets. It'd be helpful if we can dim the lights. I don't know if we can do that because they're washing out the display a little bit. We're looking right now at the inner planets. We're coming out here and we can see out to the orbit of Pluto. When I grew up, Pluto was a planet. It's not anymore, and I'll give you a little reason why. Asteroids on. So now we're looking at, see all those little white dots? Those are all asteroids similar to Pluto in their orbit, and that they're fairly eccentric. And we either had to promote all those to be planets too, and you'd have to come up with a very long sentence. My very exceptional mother just made us, 2,000 pages of documents to remember the planet's name. So that's why Pluto got demoted. Solar system overview. we're going to fly back and orient ourselves based on the solar system right now. And so we're going to take you from where we're at here. Let's see, time really, really fast. Time super fast. Well, maybe it's not fast enough. Time faster. Time really, really fast. Okay, well, we'll have to get time going really fast because we have a limited amount of time here. So I'm going to take you now outside of the Milky Way. This is our home galaxy. From the inside out, we just see kind of through the band of it, and it looks like a ring around us in the sky. But this is an artist's conception actually created by a science program, Spitzer Science Center, Dr. Robert Hurt. And it is, since we can't actually go outside our galaxy, we have to sort of reconstruct it from the inside out. But now I'm going to take you out to the large-scale structure of the universe. And this right here is 1 million galaxies from the Sloan Digital Sky Survey. And we're actually able to come in here and take a look at the structure of the universe. And not that it looks like an hourglass. That's only the fact that we're looking through the north and south of our galaxy, because looking through all the dust lanes is very unproductive. But this lets us actually look at the structure. If we right-clicked on any one of those galaxies, we could actually jump to the Sloan Digital Sky Survey data page on that and look at every observation. So I'm going to come in here and show you that besides being a time machine by going light years away and seeing things, we can also look forward in time, and we're going to go to August of 2017 on planet Earth, and within a day's drive of pretty much everybody in the United States, we can see the solar eclipse of our lifetime. So right here, we're showing you a simulation of the moon's shadow crossing the United States, and it's going to come in somewhere around Oregon. And as you can see, we have time sped up, and you can watch the satellites as they're orbiting in kind of hyperspeed. But what's making this happen is the alignment. So if we come out here right here, we can see that there's the shadow of the moon, and we can come out and see right here that the moon is aligned there, and come out further. And see the moon, the Earth, and the sun all in alignment, and that's what's giving us that eclipse. Sky mode. Now we're going to come in here and we're going to take a look at some of the imagery that's been captured. And this is the North American Nebula. And right here, we've captured this. This is the largest seamless panorama of any single subject matter. It's an all-sky image. That's 1 trillion pixels. And it lets you see 1 arcsecond per pixel anywhere in the sky. We're going to go take a look at one of the Hubble images. We're going to go ahead and say, constellation figures on. Maybe it's figures on. Oh, well. It's like my kids never listens to me. Okay, here we go. So here's the constellation, Ursa Major, and the Big Dipper. And we're going to go fly up here and see a Hubble image and show you the resolution that we can get. And this is a, how many pixels? 90 million pixel image. And we can zoom into it. And this computer was built fresh for this. So we're actually downloading the image on the fly over the internet on the shared wireless internet right now. So there's over a petabyte of information that you have access to. And you can come in here and explore star-forming regions that are 25 million light years away. And that's pretty far. So you can get this at worldwidetelescope.org and enjoy it yourself, whether you're an educator, a researcher, or just want to explore the universe.
Thank you, Jonathan. That concludes our panel. We're going to take a few questions. And I just want to remind you, once again, you're going to have the highest density of astronomers and engineers that you ever had in Austin, I think, other than probably the astronomy department at UT. Just for the end, until the end of today, across the river at the Lund Center. So please come and ask all the questions that we're not going to be able to answer today. So if we have any questions. I think someone's running around with the mic, I think.
So that was pretty much awesome. My mind is completely blown. We need to get these in our schools. How is this going to happen? Is there some kind of plan in place to do this? Is there maybe like a Khan Academy, learning device that we can implement? I mean, what's going to happen to make this widely known and available?
Well, let me answer on behalf of the Space Telescope Science Institute and our team here. We, on the Hubble, developed a long tradition of making sure there's a lot of education material, and we're just starting with the James Webb. And in fact, this idea of the Khan Academy, we're just nodding, that's a really good idea. We'll try and get a lot of these onto videos for everybody. The James Webb gives us a new opportunity, and all these tools that you're seeing, to distribute these discoveries to everybody. I mean, the whole idea here is to make everything available to everybody. So kids in the classroom can change the world themselves using data from the Hubble and the James Webb Space Telescope.
There's also some teaching resources on worldwidetelescope.org and Worldwide Telescope Ambassadors program. The Worldwide Telescope Ambassadors was done by Harvard and WGBH in Boston. And they've worked with bringing retired astronomers and volunteer astronomers into schools to help teach astronomy using Worldwide Telescope.
I guess I want to underscore another point, which is, the ability for Jonathan to demo this, the ability for any of us to show you all these images is tremendous, also because any single thing you've seen is available free to the public. So.
Can we make it mandatory?
One last thing I forgot, we are in Texas, and a few years back, a professional organization for IT volunteered a bunch of time and created a whole curriculum setup for Texas using Worldwide Telescope, and so that's also available.
A bit of a banal question, but you said you're going to place this new telescope a million miles away compared to the 100 miles of the Hubble. So what happens if something goes wrong?
It's a great question. I think what's so important about the James Webb Space Telescope is that integration and verification processes that go into it. I think part of what does take time is making sure that you are testing every piece incrementally. So you don't put everything together and then try it for the first time and wonder what it was. Every piece incrementally is tested, verified, and then put into a larger subsystem and tested again. And that's the way you're able to make sure that everything will work. Also very fortunate on the James Webb Space Telescope to have some of the best engineers and scientists around the world, and a lot of the same people that have lived through a lot of tough problems. It's not a lot of people doing things for the first time. There's a lot of lessons learned and a great team and a lot of thought going into that.
I mean, in fact, the James Webb will spend 2 years in Texas at Johnson being tested to use the optical part, going through to make sure that whatever happens when it gets out there, it does actually work.
Well, fascinating talk. Thank you very much. I would like to be a little provocative here. I saw a talk here at SXSW 2 days ago by the Nobel Prize winner Steve Weinberg, and he was making the case for a $10 billion linear accelerator. And he said, this is a fraction of the cost of what we spend in a year in manned exploration of space, including the space station, etc. which has not brought us a single scientific discovery yet. And he was willing to defend that assertion. So what do you guys have to say about it?
Stephen always has a very interesting perspective. The first thing you have to realize is a lot of the technologies, that early picture of the moon, would not have happened without the human spaceflight program. We wouldn't have had the Hubble Space Telescope without the human spaceflight program. In fact, astronauts have now gone back 5 times to actually service it. And so what actually makes these incredible technologies possible is actually a partnership between the nation that wants to do other things with NASA. You know, I mean, NASA itself is not a science agency. You know, it's a National Aeronautical Space Agency. And so we're fortunate that as scientists, we're able to leverage off that enormous investment that other people make to do science. We don't have to pay for all those technologies ourselves. You know, Northrop Grumman has a lot of other customers and just the scientists. But because these technologies get developed and get used, this whole unfolding technology, there is no way science could ever afford to actually produce those kinds of technologies. So it's this unique partnership between what I would say the scientific interest and this industrial base of the United States that makes these amazing missions, whether it be the Hubble, which everybody thinks is a wonderful success. There isn't probably a classroom in this country that doesn't have a picture, a Hubble picture on its wall. That would not have happened without the human spaceflight program.
Thank you. Keep carrying on.
Last question.
Mr. Fay, I just wonder if you've given any thought to, what kind of project you'll be working on when around the time that the data starts coming in from the Webb Telescope. You're going to be developing something for a Google Glass or something. We got an even more involved augmented reality experience.
I think you first got the intro that I work for Microsoft. But we certainly, we're actually forward-looking with a lot of programs. Microsoft Research is working with Gaia, with the European Space Agency, which is another satellite that won't see data for quite a while. The LSSD program, et cetera. And so what the reason we're in research, bringing computer science research to science is computer science needs astronomically hard problems to solve in order to find new techniques and new ways of doing things, visualizing databases, etc. And where else do you look for astronomically hard problems than astronomy?
So if you want to ask more questions, please come across the river. We're going to be alongside there all day.